Modern life relies on a continuous supply of petroleum. From the fuel in your car to the plastic in your phone, almost every consumer product begins as a raw flow of crude oil. Below the sea floor, oil is trapped in rock fissures under extreme, volatile pressure that is constantly pushing to reach the surface. When human engineering fails to contain that force, the results are explosive. The 2010 Deepwater Horizon blowout serves as the ultimate case study in containment failure. A total loss of control leads to environmental devastation. Millions of gallons of suffocating crude can coat entire ecosystems, causing damage that lasts for decades. To manage these risks, engineers deploy multi-billion-dollar megastructures. These isolated platforms are specifically designed to withstand the brutal conditions of the open ocean while tapping into the deep earth. These steel islands are inhabited by hundreds of workers who live and work on site for months at a time, maintaining 24/7 operations in one of the world's most dangerous environments. Extracting offshore oil is a calculated war of containment. Every component on the rig is part of a multi-billion-dollar system designed to hold back violent subterranean forces. Before drilling can even begin, these platforms must hold their position against Category 5 storms and waves 30 meters high. The process starts with a rotary drill. A bit made of industrial diamond or tungsten carbide grinds through miles of rock to reach the oil-bearing reservoir. This diagram illustrates the first line of defense, drilling mud, an engineered chemical mix pumped down the wellbore to balance the reservoir's upward pressure. If this mud fails, underground pressure overpowers the well, triggering a blowout where oil and gas surge violently to the surface. The final failsafe is the blowout preventer on the seafloor. This massive valve physically crushes and seals the pipe to stop the surge. The rig's survival depends on these underwater pressure systems functioning perfectly under immense stress. Once the drill successfully taps the reservoir, the natural subterranean pressure forces a violent, high-speed surge of raw liquid toward the platform. The extracted liquid is a volatile, toxic mixture of crude oil, natural gas, salt water, and sand. To unpack this mixture, the platform uses the three-phase separator. This diagram shows the internal mechanics of the massive drum as raw fluid enters. Inside, gravity and pressure separate the components. The heavy, toxic wastewater settles at the bottom, where it's treated and removed. The valuable crude oil forms a middle layer, while explosive natural gas rises to the top to be siphoned off or flared. Without this immediate separation, storing the raw extraction would be impossible and lethally dangerous. The processed crude is moved to a floating production, storage, and offloading vessel, or FPSO. This ship-sized warehouse stays anchored near the platform to hold the oil until a transport tanker arrives. This thermal visualization shows the primary storage challenge. If crude oil gets cold, it solidifies and ruptures pipelines, so active heating systems maintain an elevated temperature. A centralized control room monitors the tanks continuously. Data sensors track every change in pressure and volume to ensure the volatile cargo remains completely stable. The financial stakes are absolute. A single transfer can involve up to 2 million barrels of oil. Even a microscopic error in the custody transfer meters represents millions of dollars in lost revenue. Offshore storage is an active, precarious holding pattern, keeping a billion-dollar asset stable in the middle of a moving ocean. When the transport tanker arrives, the scale of the operation becomes clear. This very large crude carrier carries enough fuel to power an entire region. Docking these two massive vessels in open water is a high-risk maneuver. Specialized marine pilots manage the approach to prevent a collision that could trigger a catastrophic explosion. The ships lock together using steel mooring lines weighing 100 kilograms per meter. These lines dynamically adjust to ocean currents, holding the hulls perfectly parallel. Once secure, the cargo hose is connected, forming the sole umbilical cord where oil flows. 5,000 horsepower pumps then move 8 million liters of oil every hour. The entire transfer is conducted under strict no-spark protocols, as the slightest friction could ignite the entire load. The energy that powers the modern world is bankrolled by this process. It is a relentless, high-precision heist executed by thousands of workers against the most hostile environment on Earth.